Ada dengar bunyi pelik-pelik tak? Sebab saya buka kipas dekat dengan saya ni. Is it clear atau you ada dengar bunyi?
Clear.
Clear, sir. Tak ada dengar apa-apa.
Tak ada dengar angin.
Okay. Sebab panas sangat. Saya terpaksa buka kipas dan aircon. Okay, so the first unit is just an introduction before we go into the types of analysis. Chapter 2, Chapter 3 and so on will be on the analytical methods. So the first unit will be on introduction to pharmaceutical analysis. The code is BPH 2184 and what will be covered in this unit is first we will see types of analytical techniques, and these are further divided into qualitative and also quantitative, and also instrumental and non-instrumental analysis, and lastly you will see significance of the quantitative analysis in QC, and also I've included extra explanation on the method development of pharmaceutical analysis, and also the validation part, which is quite important, especially in pharma industry, pharmaceutical industry. The method development and the method validation are very crucial, especially if you want to get your product registered with the authority. In Malaysia, it is under the National Pharmaceutical Regulatory Agency, NPRA. So, first on the types of analytical techniques. So actually pharmaceutical analysis falls under the analytical chemistry branch, because most of the tests that you are going to do in pharmaceutical analysis are actually chemical analysis, and also some of the instrument involve all those instrument that is used in analytical chemistry itself, like IR, UV, what else, NMR. Okay, so these are actually procedures. Okay, analytical techniques are procedures that you can use to determine. Okay, you can determine several things. One, you can determine the identity, the constituent, purity, and stability, structure, and also the composition of a specific substance in a drug or in formulation. Okay, so this is more or less the definition for pharmaceutical analysis, because it focus on the drug formulation itself. When we talk about analytical chemistry, it's very broad. Your sample can be anything. You can take food sample, or you can take water from the drain sample. So to focus on pharmaceutical product, so the name has been changed into pharmaceutical analysis. Okay, and it can be divided into either qualitative. So qualitative, you just want to determine identity, okay, of that particular analyte or compound itself. Whereas in quantitative techniques, you want to quantitate, you want to know exactly the amount, the concentration maybe, or the purity of that particular active pharmaceutical ingredient, so on. And these two qualitative and quantitative techniques, you can do it either by instrumental or non-instrumental, meaning that in instrumental, you are using instrument machine, like a pH meter, for example, UV spectroscopy, and then HPLC, high performance liquid chromatography, or GC, or mass spectroscopy. So there's a lot of instrumentation for analysis. While for non-instrumental, another name we call it as wet analysis, because the test that you are going to do is a chemical test, wet test. Example, what you have done, I think last semester, the organic lab session was done virtually, but in your organic chemistry 1, the last experiment, which is the qualitative determination of unknown organic compound. So that is an example of non-instrumental techniques in which that you do all of the testing using chemicals and reagent. And what you call that, the amount of sample used and the amount of reagent is just stated normally in the method as like not to be exact. It's just 1 or 2 drop. Okay, it's not like add exactly 1 ml or 2 ml. So that when the method is very specific in terms of the amount to be used, then definitely that is more on the quantitative. So some of the terms that you will encounter throughout the module of pharmaceutical analysis is analyte. Analyte is actually the component of a system or a mixture to be analyzed. Let's say you have a drug formulation. Normally in a drug formulation, it contains more than just the API. Okay, the active pharmaceutical ingredient. You have your excipient, you have your probably coloring agent, maybe some sweetener to make the formulation less bitter or something like that. And then you might also have the coating. Okay, once if you want to do the analysis, all of the let's say you have a tablet, that tablet needs to be pulverized first. So all of that component will get mixed together. So the focus of your analysis will be just on one thing. Probably you just want to determine the concentration of the API. So that API itself will be called as the analyte. And then the analysis. Okay, analysis is the process of breaking a complex or substance into smaller parts in order to gain a better understanding of it. And then method. So method is very important in analysis because you have to follow a certain method in order to obtain the results. So let's say the method has been stated as so and so by your previous colleague, for example, if you go work in an industry. So you must follow from step 1 until step number 10, for example. You cannot simply jump. Okay, let's say you want to do step number 3 first and then go back to number 2. So you must follow accordingly. So it is a systematic procedure, technique of or way of doing something, especially in accordance with a definite plan, okay, which is the ordered sequence of fixed steps. So this must be followed. Later we will see why you must follow this method exactly. So this is just like a mind map, not like a mind map, but a simplified version of analytical chemistry. But here, basically, you can also replace it with pharmaceutical analysis. So it can be divided into qualitative and quantitative. Okay, qualitative can also be done using wet analysis. Quantitative also can be done using wet analysis, and you have this instrumental analysis in the middle, which is it involves either optical method, separation method, electroanalytical methods. Optical method example, all of those that involve lights like UV, IR, okay, fluorescent. So that is that falls under optical methods. While separation will be chromatography. So any chromatographic method like liquid chromatography, LC, or paper chromatography, PC, TLC, thin layer chromatography, HPLC, and also GC will fall under this, in which that a mixture can be separated first. Okay, it can be separated, and then you have electroanalytical methods. So this one definitely involves some electrical current, like in pH meter. pH meter, actually, the rod that you dip into the solution is basically an electrode. Okay, you are dipping an electrode into the solution. So that is an example of electroanalytical methods. And also electrophoresis. I think that will be covered in the last unit. So it use electrical current to separate the compound that is in the sample. So in qualitative analytical techniques, okay, we see this one first. So it is more on to the identification of components or separation or elucidation of structures. So example of identification is just you want to determine the element of a particular compound of your choice. And you can also use it to detect impurities, the API, and functional group present in a sample. Example of the analysis type is electrophoresis, flame photometry. This one can be used to determine metal that is present in your sample. In fact, different colored flame will tell you different types of metal present. Okay, the what to say, the application, other application of this is in fireworks. So if you look at the, not like normal firework, the fireworks that during Merdeka tu, so it give out different colors. You have blue, green, red. That is caused by different types of metal present. So the concept in analysis is falls under this flame photometry. And then you have fluorescent spectroscopy. This one also detect whether a compound has fluorescence properties or not. And then IR to detect functional groups, and thin layer chromatography, and also paper chromatography. In our lab, in KPJUC, we have HPLC, GC, UV, and also IR. So if you guys manage to come back to campus, so we will have a chance to do an experiment or to do an analysis using the IR instrument. And then separation, okay, as I said earlier, it involves all type of the chromatographic method, okay, paper, TLC, GC, and HPLC. Okay, there is a difference between liquid chromatography and also high performance liquid chromatography. This one I think will be covered in unit 4. Liquid chromatography is actually manual, whereby you have to pack the silica gel manually into a glass column, while this HPLC is like automated using a very expensive instrument. And then elucidation of structures. So the word elucidation is actually you want to determine the structures of the compound. Okay, if you still remember the organic, qualitative organic compound that you do in the lab session of organic chemistry, if you have the ability or the chance to use an instrument, okay, like IR, NMR, and mass spec, we can actually determine the exact structure of that particular compound, because this IR will tells you the functional group without doing any tests, without doing using any chemicals. You can straight away know whether the compound contain carbonyl group or carboxylic acid C double bond OOH, whether it is an alcohol, it contain imine bond, or whether it contain amino. So in mass spec, this can tell you with regards to the molecular mass. And the NMR, there's several types of NMR. The most common will be proton NMR or H1 NMR and carbon-13 NMR. So proton NMR will tell you the number of hydrogen available in your compound, while carbon-13 will tell you the number of carbon available in the organic compound. But the results obtained will appear in the forms of peak, okay, peaks like in a graph. So you have to know how to interpret the data. Okay, it doesn't simply you put your sample into the instrument, it will tell you straight away, oh, this compound contain 11 hydrogen and so on. no, you have to know how to interpret the data. And one more thing, you have to know whether the data that you obtain is good or not, meaning that the peaks are suitable to be interpreted. Later, if we have the chance to do the lab session, I will explain more on that. And also the last of the qualitative is the determination of physical constant, which involve melting on boiling point. This one, I believe we have done. This is the first experiment in organic chemistry 1, in which you determine the melting point of a solid compound and the boiling point of liquid compound. And this is a polarimeter. Is used to determine whether the compound can rotate plane polarized light, which result tells you whether the compound is chiral or not. Okay, so in drugs, it's very important to know whether the drugs, some drugs needs to be chiral, some doesn't have, like what do you call that, omeprazole. Okay, there is two enantiomer. One is like the normal omeprazole, and if you purchase esomeprazole, that is the one, it only contain one of the enantiomers. If the medicine or the drug is just written as omeprazole, that means it contains both sides. Both sides, both enantiomers, R and L. And then you have specific gravity, refractive index. This one also is just using an instrument, but it gives you the physical constant or physical properties. Okay, whereas in quantitative analytical techniques, okay, these involve numbers. Okay, meaning numbers, you want to know the exact quantity or amount that is present in the samples, or normally they are stated as concentration. So among the component that you can determine is the active ingredient, the API, other elements present, and also impurities. So if let's say your formulation contain impurities, you have to determine. First, you have checked using the qualitative analysis. You know your compound contain an impurities, but then again you have to quantitate that impurities so that it doesn't exceed the allowed amount. Okay, normally the parameters are already given in pharmacopoeia and so on. So you just have to follow that it shouldn't be exceeding that values. So example of analysis that can be used to quantitate is HPLC, GC, and then you have biosensors for biological molecules. So this one is mainly biological samples. And then UV-vis titrimetry. This one is titration or volumetric analysis, and also electrophoresis. But once you do quantitative analysis, you are basically doing qualitative analysis as well, because you not just only determine what it is or the identity, but you already you go further by determining the exact quantity or the exact concentration. So this is just a comparison between qualitative and quantitative analysis. Now on to the next part, which is the non-instrumental and also instrumental analysis. So you have to know how to differentiate. So the first example of non-instrumental is gravimetry. This one actually involves the difference in terms of weight and also heating. So first, normally you have to weigh the sample. Okay, you have your sample, you weigh, and then you heat the sample, probably in an oven or in a crucible. You heat it and take it out and weigh again and see in terms of weight difference. Okay, this is non-instrumental. The instrumental part with regards to gravimetry is called as the TGA, thermal gravimetric analysis. That is by using an instrument. The normal way is just by weighing the sample manually on a analytical balance, and then you have to heat either by using an oven or direct heat by putting it in a crucible. And after that, you have to weigh again. But by using the thermal gravimetric analysis, which is instrumental, the weighing process and the heating and the data is all collected by the instrument. And then titration or volumetric analysis also falls under non-instrumental because you are basically using glass apparatus and also chemicals, and you have to manually do the titration yourself. Okay, and also look for the color changes. So this also has been there is a version where it is automated, which is called auto titrator. Basically, the titration are done autonomously, so you don't need to wait at the site. You just set, and then the solution from the what do you call that, burette will drop in automatically, and it will stop. It doesn't use any color indicator, but then again, it also includes a pH meter. So, for example, in acid base, you know that if you're using strong acid, strong base, the endpoint should be pH 7. So at pH 7, once the pH meter detected it has reached pH 7, then the titration will stop. Okay. And then this is volumetry in terms of how much gas is being evolved, meaning produced gas, the reaction produced gas, or whether the reaction absorbed gas during the reaction process. For instrumental analysis, this one, there is a wide range of instrument that we can list. So I just list some of the most common and the one that will be used a lot in terms of pharmaceutical analysis. Can be divided into several categories like optical methods. So this one, by the measurement of radiant energy. Okay, EMR is electromagnetic wave, okay, like UV, IR, all those things, of a particular wavelength being either absorbed or emitted by a sample. So this includes UVVs, IR, NMR, Raman spectroscopy, mass spec, nephelometry, and turbidimetry, refractometer, flame photometry, colorimetry, polarimetry. And then in electrical methods, you have potentiometry, conductimetry, voltammetry, and coulometry, and all those separation techniques, which is the chromatographic methods. Okay, these are among the three main categories of instrumental. Then the last, which is the physical methods, which you are actually measuring the physical properties of that particular sample. You have this DTA, DSC, differential scanning calorimetry, are normally done to determine the melting point, the exact melting point. We actually can calculate the delta H of the process. Okay, and also in thermal, mechanical, and gravimetric analysis, we can see when or at which temperature your sample will start to melt and also start to decompose. Decompose meaning that normally in organic compound, once you heat, normally in TGA, the sample will be heated up to 900 degrees Celsius. The sample will end up to become carbon, just carbon, very like black carbon. Okay, so from here we can see at which temperature the sample start to decompose. Okay, normally if it doesn't contain any metals, it will start to decompose. For most organic compound that I have tested myself, it start to decompose at around 200 degrees Celsius, or maybe slightly more than that. And you also have these hyphenated methods. So hyphenated actually involve two types of instrument which is connected together. Like the first one, you have GCMS. This is gas chromatography combined together with mass spectroscopy, meaning that in GC, your sample will get separated. Once you inject the sample mixture, it will get separated first, but the detection or the analysis are further done by the mass spectroscopy. And then you also have this GCIR, is connected to an infrared spectroscopy. And then you have MS. MS is mass spec. And this one, even there is more than two, which is three. You have LC, the liquid chromatography connected to mass spectroscopy. So that are the types of analysis, or the types of analytical methods that are available to be selected in order to do the pharmaceutical analysis. Depends on your sample. But then again, out of all of that analytical methods available, you yourself have to develop a method which is suitable to be done first in your lab, okay, because you cannot go simply to like other people's lab. So it must be doable in your lab. So it must suit you. Let's say your lab doesn't contain an IR instrument. So what's the point of having to know the IR method, right? So you must know the limit of the capabilities of the lab that you have, and also what kind of chemicals that is available. So once you have all of that, then only you can develop a suitable method that is doable. So method development is a step process that determine test method capabilities through selection and optimization of analytical test parameters. So it will provide you with high degree of assurance that the test method will meet or surpass the established requirements. It also tells you whether the method developed should have been validated appropriately before use. Okay, once you have this method to be used, for example, to do the assay of a particular drug formulation. So that method has to be validated first. Later we will see what falls under the validation part. And then as the method development proceeds, so regular review should be carried out. That means you should always look back on what you have done earlier. Okay, whether there's still some changes you might need to do, or there could be optimization steps that can be done to make the test method more robust, or it can give you more accurate result. So to develop an analytical methods, so it will depends on several things. So several factors. First is what type of sample that you want to analyze. So this will tells you what kind of analysis that is suitable for that sample. Let's say you have a liquid sample that is non-volatile. So that cannot be used in gas chromatography. Okay, for gas chromatography, only volatile liquids sample can be used. If you use non-volatile, even if you heat the sample, it won't turn into gas. Okay, so then the target. Okay, what do you want? What is the goal of that analysis? Okay, why you want to do it? And whether the samples need to be recovered or not. So meaning that after at the end of the analysis, do you still want to collect the sample or it can be discarded? And also matrix effect, signal to noise ratio, and standards. Okay, so once developed, all of the method needs to be validated before it can be applied or used. So types of sample, okay, there are several in which that you have to study, which is the sample being organic or inorganic. So inorganic, probably some of the sample will contain metals, okay, like iron sulfate, okay, in what do you call the antacid. Some of the antacid will either contain aluminium, right? Aluminium. So this falls under inorganic. But if it's organic, then it just contain most of the API will falls under organic. And then chirality. So this can be test using polarimeter, solubility, whether it can be dissolved in polar or non-polar solvent, and the sample whether it is solid or liquid. So this has to be taken into account before you select the most suitable method in order to analyze it. So these are some of the example of biological samples. Okay, biological meaning coming from human. Okay, depending on the purpose of your test. Like for example, if you want to check the DNA of a person, you can take the sample from the cheek tissue. Okay, no need to have a urine test, because normally urine test you do it if you want to check the content of drugs, okay, or in fact, and also maybe alcohol level. Even in alcohol level, you can just do using the breathalyzer test. Okay, it will tells you whether the person is intoxicated or not. Okay, so depends on the users. So these are some of the biological samples and how the samples are being extracted. Then the aim, okay, or the target. So why do you want to do the analysis? Okay, whether it is just to separate, okay, or if you want to elucidate the structure, the whole structure, you want to know exactly what is the structures, or just you want to know the number of components available. Let's say in this particular formulation, there are 6 components. So that's it. You don't want to know what is that 6 components. So the target will determine types of analysis that you need to do. And if it used to check impurities, the purity of the compound, or you just want to detect, or whether you want to quantitate. Okay. Then another thing that you have to know is the matrix effect. Okay, matrix effects. So matrix is actually the component of a sample other than the analyte of interest. So let's say you have a formulation of drugs and your analyte is actually the active ingredient, the API. So the rest of that is considered to be the matrix. Okay, so matrix can have an effect on the way an analysis is conducted and the quality of the results that you get at the end of the analysis. So these are called such as matrix effect. It is like the other things beside the analyte will give you slightly different result than the actual. So this can be overcome normally by using blank. Okay, example that I put here is in UV spectroscopy. Normally, you don't straight away put the cuvette containing the sample into the UV instrument. First, you have to measure the blank first. And the blank are normally uh, the solvent, okay, that you use to dissolve the solute. So here, when a particular solution is made of solvent X, let's say ethanol, you use ethanol. So just before each sample that is being analyzed, so a blank reading using only solvent, the ethanol will be taken. So only after that, you can start measuring the sample. But let's say the next sample that you want to measure use different kind of solvent, let's say water, so you have to redo the blank measurement again. Okay, so blank, if the blank is the same for all sample, then you can just straight away proceed with measuring the sample. So when the actual sample is tested, okay, when you put the sample, so the reading shown or the value given will be after deducting the absorbance caused by the solvent. Okay, in IR also there is a blank measurement, so need to be done before you can measure the sample itself. Then recovery. So in terms of recovery, so you have to ask whether the sample that you use for the testing is still needed after the analysis, or whether it can be discarded. So many analytical methods are destructive. So meaning that once you use it for the analysis, it's considered to be gone already. So you cannot collect it back. So in many scenarios, the sample to be analyzed will only be available in small amount. So this is how to say most common in when you have when you do research. Okay, when you do research, let's say you synthesize a new compound, so the available compound that you have will normally be in small amount. Okay, unlike in industry, the sample that you want to test are normally bulk. Okay, you have quite a lot. So in this case, the sample has to be retrieved after analysis for further studies. So some of the example of destructive and non-destructive methods, most chromatography techniques, because it gets separated altogether. Okay, and then IR. So IR, the most common method is the using potassium bromide disc, KBr, or Nujol. But there's also one non-destructive methods for IR, which is you have to put what we call as the like an accessory to the IR instrument, which we call as ATR method. Okay, the attenuated total reflectance that will be attached to the IR instrument, and you can straight away take a sample and put on top of the there's a sample holder, and the measurement can be taken straight away. And after that, the sample you can collect it carefully, and it can be reused again for other analysis. And non-destructive methods, NMR, fluorescent, UV. So all of these, after the analysis, the sample can be kept again. Okay. So this is the signal to noise ratio. So this is also a term that is most common for analysis that gives you result in terms of peaks, like IR, spectrum, UV spectrum, chromatogram. Okay, it is basically, if you look over here, the ratio of the strength of the signal, okay, or the electrical signal for your sample, and also the unwanted interference over here, which we call it as noise. Okay, so the best is to have large SN ratio. So if you have large values of signal to noise ratio, that means you have very strong signal of the samples, a strong peak over here, or the noise is very, very small. Okay, so always check your method, the results obtained, it has very good SN ratio. Okay. And then you have also need to know on standards. So standard is very important in not just in pharma industry, but in other analytical chemistry as well. So standard basically are converted into this standard solution. So a standard solution is a solution containing a precisely known concentration of an element or a substance. Okay, it can be used as a control or as a reference. Okay, you have to refer when you do an analysis. You have to refer to something. Let's say you are given formulation of uh, chloroquine, for example. So you take the tablet, you pulverize it, and then you dilute in solvent, and you run into the HPLC machine. So it'll give you probably there could be 3 peaks, but which peaks can be identified as chloroquine. So you cannot tell, oh, the second peak. So this has to be done by referring to a standard. So a standard is something that you already know the concentration, the identity. So it needs to be measured first, so that when you do your sample, it can be straight away refer. Oh, the second peak, which is appearing at maybe 5 minutes, is the peak that we can say as the chloroquine, for example. So there are types of standard. One is what we call as primary and secondary standard, and also internal and external standards. So a primary standards are substance of known high purity, which may be dissolved in a known volume of solvent to give a primary standard solution with accurately known concentration. So in pharma industry, normally the primary standard are purchased from pharmacopoeia companies of suppliers like BP, British Pharmacopoeia, or USP. And they don't sell in bulk, because you are actually buying the API, active pharmaceutical ingredients, which are being synthesized, okay? And the purity are very high, and it costs I think several thousands for just a small amount like 10 milligram or 20 milligram. Okay, so it has to be used wisely. And in industry, which is of course their purpose is to make money, so it is not feasible to do the testing every time you need to do the analysis. You have to use the primary standard. So this comes where secondary standard comes in. So a secondary standard is a standard that is prepared in the lab for a specific analysis. So normally it is standardized against primary standard. So what happened in the industry, normally the raw material that is being used to create that formulation or the drugs that you want to sell are going to be tested or standardized. We use the word standardized against the primary standard. Okay, so let's say the raw material that you use has the purity of 99.8%. So that has to be noted, so that once you do the analysis for the rest of the other samples, the purity of the standard that you use can be calculated correctly. Okay, and the secondary standard also is known as working standard, and primary also known as reference standard. Okay, so these can also be known as reference standard, and secondary standard can also be known as working standard. And the internal and external standard. So internal, meaning the word internal, that means the standard itself is being included in the sample. So this is a chemical substance that is added in a constant amount to samples, the blank and calibration standards in a chemical analysis. So this is done to correct for the loss of analyte during the analysis. So for example, adding a fixed amount of standard into negative control positive control and every sample analysis. So any reading obtained that shows deviation, then the amount of standard added will apply to the sample as well. So it also used when analytical technique has not been properly validated. So internal standard can be done. Later we'll see in the validation where the sample has been spiked. Okay, the word meaning we put more a known amount of this analyte of interest into the sample. Then we have the external standard. So like internal standard, it is not added to the unknown. So you don't add it into the sample. So it is analyzed or you run it separately as it is. And these are done normally at different concentration. So you can generate what we call as the standard curve. Okay, so standard curve like this. Actually, it is not a curve. You must get a straight line, but this is just for the namesake. It is called as a standard curve or a linearity test in which that you want to get a linear plot. So the standard curve will be used as reference for all analysis that is done afterward. So if you look here in this picture, so this sample has very dark blue color, while this one is clear solution. So this has the highest concentration of that particular compound, while this one has 0. So what you have to do is you have to do a serial dilution. Let's say this concentration is maybe 5 molar. So you do a dilution, maybe half and another half, another half, and another half. And the point is each of these different concentration will correspond to the expected reading. For example, over here, the peak area is the area under the graph. Like, for example, in this, where is it? Okay, this is the chromatogram. So the concentration of that particular compound can be calculated by this area under the curve. Okay, so here in this graph, so let's say here you have your 5,000 mg per liter concentration. If you double by right, the peak area should correspond to that value as well. And once you plot a graph like this, you should get a straight line. And the most important is the R squared value, okay, which can be obtained easily by using Excel. The values actually different reference give out this different specification. Back when I was working in the industry, my employer requires the R squared value to be 0.99 x, meaning that 0.9901 and more, because the maximum value is 1.0. Okay, but certain journals they said that the acceptable value is from 0.98 and above. So it depends, but it is better to have the R squared value closer to 1.0. So if you get to 1.0, then the standard curve is how to say, as high accuracy. So these are the method development plan itself. Okay, it involves 6 steps. Okay, the first, which is the studying of the sample. Okay, establish your method goals, the literature review, and you have to select which method that you want to use, and then you can further optimize the method. Then last step will be to finalize it. Okay, you have to finalize the method itself. So, one moment. So before I go into this, do you have any question with the previous part? Ada soalan untuk part yang sebelumnya?